Dear students, today we would like to discuss two problems that is very important for the statistics, and these type of problems can be seen in your UGC net examinations. So that is very important. So you can expect this type of transformation problems. So we are studying how can we solve this type of problems. That means we are finding the distribution of transformation using some other variable. Okay, we have two variables, that is, for example, in this example 7.11.1 we have two function. What is x1 and x2 are independent random variables and they are having standard and normal variables. So the joint density function will be 1 by root 2 pi into 1 by root 2 pi e raised to minus 1 by 2 x1 square into e raised to minus x2 square. So that can be written like this: 1 by 2 pi e raised to minus 1 by 2 into x1 square plus x2 square minus infinity less than x1 x2 less than. That means the variable lies between minus infinity and infinity. Okay, we now define two transformation, that is y1 is x1 plus x2 and y2 is x1 minus 2x2. So this is transformation. x1 and x2 is transformed into y1 and y2. This type of transformation is very important in statistics. We can see later on, you will study in detail this type of transformation and this method of finding the distribution of this type of transformations. Okay. So let us use the previous theorems we have discussed till date. That is, we are considering y is equal to g of x. General form of the transformation is y is equal to g of x. So g1 of x is first component, that is x1 plus x2, y1. g1 of x is y1 and g2 of x is y2, that is y1 is g1 of x equal to x1 plus x2 and g2 of x equal to x1 minus 2x2. We can find out the inverse, okay, or we can solve these two equations. We can solve x1 plus x2 equal to g1 and x1 minus 2x2 equal to g2. That is two equation and two unknown, that is x1 and x2. So we can solve uniquely. That means we can find out the value of x1. So when we solve this, x1 is equal to, we know that what are the given condition? y1 equal to x1 plus x2. I will write that time. We have the transformation y1 equal to x1 plus x2. Second transformation is y2 equal to x1 minus 2x2, right? We can add it together or we can subtract. Then we can easily find that if we subtract, suppose this is equation number 1, and this is equation number 2. Okay, so what is 1 minus 2? 1 minus 2, that will result in 3x2 equal to y1 minus y1 minus y2 equal to 3x2, right? So what will be x2? x2 equal to y1 minus y2 divided by 3, right? Okay, we can substitute the value of x2 equal to y1 minus y2 in equation number 1, so that we obtain x1 equal to y1 minus x2, that equal to y1 minus, what is x2? x2 is y1 minus y2 by 3. So what is the result? 3y1, 2y1 plus y2, 2y1 plus y2 by 3, right? Okay, so that is the So that is yeah, it is given there. Given here 2y1 plus y2 by 3 x1 and x2 is equal to y1 minus y2 by 3. Okay, right. So we can find out the Jacobian of transformation. For that we will determine dou g1 inverse of g1 inverse g2 inverse by dou y1 y2. We have to determine this determinant, that is determinant of what is dou g1 inverse by dou x1, that is 2 by 3. Okay, dou g1 inverse by dou y2, that is 1 by 3. Similarly, dou g2 inverse by dou y1, that is 1 by 3. Dou g2 inverse by dou y2, that is minus 1 by 3. Okay, right. So this can be simplified as, since it's determinant, we can take the product and subtract. So that is 2 minus 1 by 3. Okay, so we can apply the formula. We have already derived the formula for finding the probability density function of the transformed variable, that is h of phi. You know that h of phi is equal to f of x into modulus of determinant of this Jacobian. Okay, so we can see that, yeah, this one, h of phi is equal to f of, not x, just x in terms of y. Okay, x in terms of y. Instead of x we write g inverse of y. So f of g inverse of y into modulus of that determinant. Okay, so we apply that formula here, and we can see that, you know, f of x is 1 by 2 pi e raised to minus x1 square plus x2 square by 2. So instead of x1 square we can write 2y1 plus y2 by 3 square, and instead of x2 square we can write y1 minus y2 by 3 square. We have substituted, and the modulus of the determinant, that is modulus of minus 1 by 3, that is 1 by 3 is substituted here, and you can see this is the density function of the y vector. Okay, so we can further simplify the further simplification is only mathematical treatment. You can do in your notebook. So just square it and add in properly, so you will get this answer. Okay, so this is the, so it is a very wonderful methodology, wonderful technique, that is using some variable we are finding the distribution of the transformation. We know the probability density function of the variable x1 and x2, so we are finding the probability density function of transformed variable y1 and y2. Okay, from this we can find out the marginal densities also. Okay, now another example is, suppose that it is decided to determine the density function of the random variable b is equal to x1 plus x2, where x1 greater than 0, x2 greater than 0, and x equal to x1 comma x2. Okay, has a continuous density function f of x1 comma x2. This can be okay. So in this case we have to find out the we have x and y, the random variables, and it corresponding joint density of x1 comma x2. We have to determine the distribution of v equal to x1 plus x2. So there is only one transformation. So in such cases we can take another transformation as a, it is considered as a dummy variable. So it is another transformation, so that we can have two variable in two unknowns, so that we will get the solution easily. So we will use a dummy transformation, that is y2 is equal to x2. So so that we will get the distribution of v. What is v? V is nothing but x1 plus x2. Now look at the distribution function, form of the distribution. What is the form of the distribution of variable v? You know, v is x1 plus x2. So the distribution function, form of the distribution function will be probability of x1 plus x2 by less than or equal to some real value. That is probability of x1 plus x2 less than or equal to v. Okay, so let us denote q of v as the distribution function of capital V. What is capital V? Capital V is nothing but x1 plus x2. Okay, so probability of v less than or equal to v means probability of x1 plus x2 less than or equal to v. In this case, so you know that the density is x1 plus x2 less than or equal to v. You know the region x1 plus x2. You know the line x1 plus x2 will be, what will be the line x1 plus x2? Suppose this is x axis, this is y axis. So x1 plus x2 will be some line like this. Okay, x1 plus x2 equal to v. Just write like this. This is axis x1. This is axis x2. So what is this line? x1 plus x2 equal to some v, right? So what will be x1 plus x2 less than or equal to v? Yeah, that will be the region below that. Let us color it. Okay, this is the region. If the random variable is non-negative, this will be the region. If the random variable is arbitrary, we have to take this region also. So suppose for the sake of better narration, we can consider this is a non-negative random variables. These are non-negative random variables. So this will be the region. So how can we find out the area under the curve in this region? Let us consider some lamina. What lamina is taken here? Okay. Let us consider lamina. Here it is a lamina. Okay, this is a lamina. You can move this lamina. First of all, we can integrate. That means we can integrate with respect to x2 from here to here. Okay, and after that we can move this lamina to another region. Okay, move this lamina to from 0 to v. x1 can be moved from 0 to v. At the same time, y2 can be moved from 0 to where it reaches? It reaches, x2 reaches v minus x1. At the same time, we have to move this lamina on the x-axis from 0 to v. Okay, so that is the methodology we are using for the integration over this type of region. Okay, I think you know the steps involved because we are studying in detail in +2 classes. So the integration will goes like this. So this is the area, region A. So this is the region A. Yellow region is A. Okay, yellow colored region is A actually. So we can integrate the function over that region. Thus, that is the methodology. So that integration will look like this. So we can move. Here they are considering in horizontal lamina. Okay, they are considering in a horizontal way because they are considering this lamina. This lamina is moved from 0 to v minus x2. At the same time, the x2 is moved from 0 to v. Okay, 0 to v. So that methodology is used in this. So x1 can be moved from 0 to v minus x2 and x2 can be moved from 0 to v. Okay, so that is the integration. How can we find out the density function? You know that is by method of differentiation. That is small q of v is equal to dq by dv. That equal to integral. We can differentiate the integration. So that is based on the theorem we have discussed in 7.10.2, interchange of integration and differentiation. Or step. So integral 0 to v dou by dou v of integral 0 to v minus x2 d dou x1 f of x1 comma x2 dx1 dx2. Okay, when we differentiate with respect to this new small v, so what we will get, this we can be applied using what is the theorem, fundamental theorem. Using this fundamental theorem we can write it as, you know, capital F dash of t is equal to small f of t. So that theorem is applied here, and it will result in small f of v minus x2 comma x2 and dx2. Okay, now so we got the density function. Now consider the transformation. What is the transformation? Yeah, y1 is equal to x1 plus x2. Okay, and y2 is equal to x2. Okay, so this is the second method. So we can check whether both these methods are result in same density. Okay, so in the first method it is distribution function and difference, we have considered distribution function of q, and this is actually the standard method. Okay, this transformation method is based on some theorems we have discussed. So this is actually theoretical method. First method is theoretical method. In the second method we consider y1 equal to x1 plus x2 and y2 is equal to x2. Okay, let us transform. So what will be x1 in terms of y1 and y2? That is x1 equal to y1 minus y2 and x2 is equal to y2. Just take the dou x1 x2 by dou y1 y2, that is dou x1 by dou y1, that is 1, dou x1 by dou y2, that is minus 1, dou x2 by dou y1 0, dou x2 by dou y2, that is 1. So that is given here, and then take the determinant, you know the value, take the mod. So that is here the value is 1 minus 0, that is 1. So determinant is 1 and modulus is 1. So we need not to consider any more term. Okay, this is, so h of y1 y2 will be f of y1 minus y2, because x1 is y1 minus y2 and x2 is y2. So x in terms of y, we have written the x variables in terms of y. So this is equal to f of y1 minus y2 into this determinant. This is actually 1, so we just need to consider this only. So the objective is to find out the distribution of v or density of v. So how can we find out the density of v? You know what is v? V is actually y1. V is actually y1 because v is equal to x1 plus x2. So in order to solve this, in order to find out the density of v, we added one dummy variable y2, and instead of v we have written y1 and used this transformation method. So to find out the density of v only, we have to integrate this joint density with respect to y1. Okay, with respect to y2, okay. So when we differentiate with respect to y2, we will get q of v is equal to integral 0 to v, because the maximum possible value of y2 is v, f of y1 minus y2 comma y2 dy2. So since it is a constant, we can write it as a v also, no problem. There is no problem with this. This is integration variables. Instead of y2 we can use x2, no problem. There is no problem associated with. Okay, so moreover we know that y1 is v, so we can replace with the y1 with the v and y2 with x2. y2 is only integration variable. There is no association with the earlier y2 we have discussed. We can consider it as an integration variable, so that we are replacing with the x2. Okay, so this is the result obtained by distribution function method. This is the method to calculate the distribution function of any transformation. This is a theoretical method, distribution function, density function. This is another alternative method based on the transformation of multivariate random variables. Okay, so in both methods we obtain the same result. So we can apply any one of this method for the computation of the distribution of the transformation of variable. Okay. Next is method of maximal likelihood. Actually, what is method of maximal likelihood says, in statistics we are using the statistical inference, and in that inference we are considering two theories. One is point estimation or interval estimation, another is testing of hypotheses. So estimation and testing of hypotheses are two branches of statistical inference. So in that inference, one of the method of finding the estimator is method of maximal likelihood estimation. So what are the steps involved in computation of maximal likelihood estimators? You will select a random sample x1, x2, xn from the population under consideration. The population may be having some distribution like normal n mu comma sigma square. So in that case we have two parameter, n mu comma sigma square, mean mu and variance sigma square. Similarly, in general we can consider there are p number of parameters, theta 1, theta 2, etc., theta p. In the case of normal n mu comma sigma square, the parameters are mu and sigma square. That means theta 1 is mu and theta 2 is sigma square. So in general we can consider there are p number of parameters associated with the distribution of the random sample. Okay. So here we consider the random vector x1, x2, xn prime, and suppose we are considering it is having some joint density function f of x comma theta. X is a vector, theta is a vector. X is an n-dimensional vector, theta is a p-dimensional vector. The density function usually referred to as the likelihood function of x, denoted by Lx comma theta. When we call the joint density function, we are assuming that x is random variable and theta is fixed. We will call the same function as likelihood function. Then we consider x is fixed and theta is a random variable. Both are same at the same time. F of x1 comma etc. xn. This is the joint density function having some parameter p comma q. Okay. So in this case we consider p is fixed and q is fixed. This can be written as L of p comma q comma x1 comma etc. xn. We have to write like this, but in this text we can see that x comes first. No problem. This is convenient to understand. This notation is convenient to understand. In some books you can see the parameter comes first in likelihood function and the variable values. So it is given. That means x1, x2, x is given. At the same time it is same as joint density function. The form will be same. For in the case of normal distribution, what is the joint density function? Suppose we are considering multivariate normal distribution. Okay. So what will be the joint density? 1 by 2 into pi. Okay. 2 into pi raised to 1 by 2. Is it right? 1 by 2 into e raised to x minus 1 by 2 into minus 1 by 2 into 1 by 2 into what will be the next values, x1 square plus etc. xn square. Square minus mu1, let us denote it as minus mu1. We are considering only one parameter, plus etc. mu2, okay. Sigma is equal to 1, so in that case we will have joint density like this. So this is same as likelihood function, but at the same time we are considering for the joint density mu will be fixed, but for the likelihood function mu is random, and sorry, mu can be okay. So if we are calling it as joint density function, we will treat x1 x2 etc. Observation, and mu is fixed. At the same time, if you are calling it as a likelihood function, we can consider mu as a random and x1 x2 etc. given value. So how can you find out the maximal likelihood estimator? I think you know the procedures. Differentiate the likelihood function with respect to the parameter and equating to 0 and solve, or otherwise we can take the log likelihood and differentiate with respect to the parameter and equating to 0. We will get likelihood equations. Okay, so these are some examples. Okay, these are some examples. So this is actually the application of multivariable calculus. Actually, we are differentiating. Even though we are differentiating, we are well aware about this type of differentiation because of this mathematical calculus. Okay, the tool is nothing but the mathematical calculus. So yeah, it is given here. The example is given here. You can take the log likelihood. You can find out the likelihood, log likelihood, and differentiate with respect to parameters and equating to 0 and solve simultaneously, so that you will get the estimated values mu cap and sigma cap square. Okay, this is the assign matrix, and you can find out whether this is maximum or minimum. You have identified 2 points, mu cap and sigma cap square. You can use this assign matrix for finding whether this is maximum or minimum. If this determinant is positive, then we can say that it is a point of maximum. Okay, sorry, if it is less than 0, if dou square L square by dou mu square is less than 0, we can say that this is the point of maximum, and the determinant of n square, secondary weight, determinant of n square, sigma cap square is greater than 0. So this is the criteria satisfied by the corollary 7.7.1. So you can say that this is point of maximum or minimum based on this Hessian matrix, determinant of that Hessian matrix. So the maximal likelihood is very fundamental and strongly required in statistical estimation. Most of the distributions can be estimated, the parameters of the distributions can be estimated using method of maximal likelihood. There are other methods available for finding the estimators. At the same time, MLE method is very common. We have to use, we can use the MLE method for finding the estimator of the parameters of the distribution. Okay, I think I think we have discussed one two examples and result, and one more examples. This is sufficient for today's session. You can study, write and try to understand, and if you have any doubt you can ask to me, no problem. Anyway, we will discuss the next section in the next class.